All right, welcome back everybody for the second part of the afternoon session. It's my pleasure that now Kristan Temme from IBM Quantum will tell us about the evidence for utility of quantum computers before fault tolerance.
Cool, thank you. Thanks a lot. Thanks a lot, Marcus. Well, thanks a lot for actually the invitation. I've only seen this room through one of those cameras for the past, I don't know how many years. So it's nice to be here in person for once. So I've never been here before. And so thanks for the invitation. Yeah, so as Marcus said, what I'm going to talk about is not a recent paper, actually, a paper that we had about a year ago. The title was Evidence for the Utility of Quantum Computers before fault tolerance. And I hope if I go through that talk, it actually becomes clear of what we mean by that and what that means. Right? And so before I go into that, I actually want to acknowledge all the people that did all the work. So on the IBM side, people that ran the experiments were Youngsuk Kim, Andrew Edens in particular. Then the big people, big names behind the entire effort, which we have to put out, was Abhinav, Sergey, and Jay, who thought about error mitigation methods as well, and so forth. But also I wanted to thank a lot of people from Berkeley who actually helped us with the numerical simulations. So there was Sajjan Yuntao and Michael Zelatel who helped us do the numerical simulations at that end. But that would be unfair to only thank these people, because there's quite a few people that got those devices to work and wrote software and did all those things. We made large-scale experiments possible for us. And yeah, so I let them be acknowledged, although they disappear in this small font. Well, can you count? So it's roughly, it should be around 900 to 1,000, roughly. I never counted all names, but I mean, length times width, you know. Sorry? I'm not, I don't know. So, right. So, okay, that said, so let me go a bit through the basics. I mean, we've talked about this morning what our entire setup is, what the motivation is, and so forth. So error mitigation has been mentioned a few times, but I wasn't asked to just make a very general, broad introduction. So what is our motivation? Sort of, we have at this point accepted defeat, which means essentially that what this means essentially is we're just given the hardware that we have, and we just try to run gates in a circuit as long as coherence times permit us. And at some point, we just stop, right? And then we want to measure some observable. And our entire goal is that, okay, whatever algorithm you want to cram into that, that's our setup, right? So you have to find anything that fits that mold. Like, so you have this much coherence time. This is how good your gates are. This is how long you run, right? And so what sent us down that path was an early experiment on BQE, which is a method introduced in the chemical sector by Alanis Buruguzik and his group, in QA/OA sector and optimization by Adifari and his group. And so the idea there is basically you prepare a state, you have a bunch of parameters, you choose very good parameters, and that expectation value at the end minimizes some energy, and then you could potentially sample from that state or so. In chemistry, you basically, yes, do that, and you want to sort of fit some curve. And so what we did is we just blindly applied that, thoughtless, and did some classical simulations. We noticed we're off by a bit. So that's a 7-qubit, 4-qubit experiment, and a very, very shallow and small circuit, 4 qubits, depth 2 or 3, however you want to count this. And so the first thing is, so why is this wrong? Well, because you have decoherence, right? And that naive picture that you could have had is, so everything is fine until I reach T1 or T2 is, of course, very, very naive. And so stuff starts to get bad from the beginning. And the only thing that we're trying to do is not sort of, as we said, we have accepted this is how long we go. The only thing that we're trying to do is within that window to get a reasonably correct answer, all right? And so that was what motivated us to think about error mitigation. So briefly after, we thought about different methods and different schemes, and we essentially proposed 2 of the earliest methods. Now there's many more subsequent methods that have followed, and people have thought about them. But I'll mostly refer to our first methods and use them. So we have 2 methods. So one that was mentioned earlier was zero noise extrapolation, which I'll explain in a bit, where the key idea is you treat your expectation value as sort of a function of the noise parameter, and then you extrapolate. And the second method is probabilistic error cancellation that we've used, okay? So to briefly explain that, let me talk a bit about probabilistic error cancellation. So we're doing something there that sounds or seems morally wrong, right? Why? So if you look at this, what that cartoon is supposed to represent, I'll go into a bit more detail later, is basically, okay, suppose you have a bunch of noisy gates and you can cleanly separate out what the noisy part is and what the gate part is and so forth. Then what probabilistic error cancellation is supposed to do is you're supposed to sit down on pen and paper, write down the inverse map of the noise channel, and apply the inverse of a channel. So why is that morally wrong? Well, because that's not a physical operation, right? But the good thing is you can implement that thing on average, right? So there's a sampling procedure where you pay dearly for the fact that it's an inverse there with an increase in variance, but there's a sampling procedure that effectively lets you implement the inverse of the noise, and I'll show you what that procedure is in a bit. The nice thing is why we actually like that one for formal reasons a bit better is because you can actually sit down and, assuming that you learn the right noise model, with minor errors in there, you can give a formal error bound on how wrong your estimate is that you produce relative to the true estimate of what the circuit should produce in the end. So there's two parts to this. So this is the painful part, this gamma L. That's a quantity that basically grows exponentially in depth, and the base gamma grows in the width. So that's sort of consistent with what Jens earlier said. But then there's a weakly exponential error that you basically get by estimating your error model a bit wrong, right? And I'll talk about that one too. Sorry?
Unitary error?
No, no. So this error basically, so there is, which unitary error, sir?
Well, it looks unitary. It looks like you're applying unitaries.
Right, so
unitary error?
No. So this is a general error across the full device in principle, and I'll talk about exactly what we mean and what noise model we have in a second, okay? Right. So that's the basic idea for probabilistic error cancellation. Then for zero noise extrapolation, what we do is the following. So the idea is basically, suppose you have some ideal circuit that you want to run, and then there's some noisy map that represents it, and that noisy map is sort of by noise continuously connected, or actually analytically connected to the ideal circuit, right? And so then you can treat the expectation value as a function of the noise, and once you can do that, suppose someone gave you a knob that would allow you to precisely always tune up that noise parameter. So you can do the best you can do at lambda. That's the best you get. That's, you had your experimentalists work all night, and that's the best they could come up with. But then you can ask them to precisely make the exact same noise a factor g worse, a factor g worse, and a factor g worse. And so there's two ways you can go about this. So one way, the way we had it originally in the paper, is basically through Richardson extrapolation. So that's actually a method that's over a century old and is being used extensively in numerics. And so if you have the promise that your function is analytic, then you have that expansion. And what you can do is basically, you can run this thing at various noise strength, and you can recombine expectation values to cancel lower orders in the expansion. And then you can give an error bound on the remainder term. That is a pretty poor error bound, but it is an error bound nonetheless. But then there's another method that we used in the experiment as well. So we used a mixture between the two, depending on how bad the variance was, which is essentially exponential extrapolation. So exponential extrapolation is you basically, rather than trying to fit a polynomial, you fit an exponential with 2 points. That was introduced by Endo, Benjamin, and Lee. And there are no formal error bounds on that, but we've noticed in experiment empirically that's actually doing quite well, right? In the setting that we considered remark, right? Okay, so where does that leave us in that setup? So in principle, since we're not running a method right now that has a formal error bound, I mean, that's going to be the goal in the end. We're sort of in the ballpark of, okay, this is a heuristic, and you have to try out how well it does and it performs, right? So you could think about, well, there's sort of a competition between methods here, or there's a way of basically trading methods off to one another. Is if you go to a sufficiently large size, you only have classically approximation methods available. So the exact solution in general may not be there. And what you could now ask is basically, in that setting, how do these approximation methods that we use in terms of error mitigation on those circuits, how well do they perform and how well do they stack up against the expectation values for other methods, right? Okay, so what we do here is basically in this paper is sort of that we're, for the first time in terms of the number of qubits and circuit depth, overall, we are sort of in a regime where you start, okay, where you can start playing this game, right? And so I think the easiest way to explain what we were trying to do and what we're going for is is an age-old computational physics playbook, right? Which is, it's just a comparison of methods. How do you start building faith in a new method that you haven't had before? Well, what you do is you take a bag of other methods that you would know, and then you go into a regime where you sort of expect to know what the answer is, and then you start comparing those methods. And if the new method sort of gives something that's reasonably consistent with the old one, you say, okay, that's fine. And then that's the essential playbook that we're trying to follow here, right? So we're going to a size later that is, well, 127 qubits, as I'll say. You run a circuit, and at that point, there's approximation methods, and now you basically have to build faith into the new methods based on error mitigation that they should work at that scale reasonably well, right? And so as an example here, so that's a plot that we've taken from PRX, I'll talk from the Flatiron group, where they basically bunch all the methods together and compare them. And I renamed them method 1 to method 11, and one of them is a quantum computer, but I'm not going to tell you which one. Right? Okay. Gotcha. So then, important, depending on what people read and so forth, we have to point out, so this is clearly not an advantage claim. This also doesn't really make sense to make an advantage claim here, and we'll talk about that even in the paper and later on. So first of all, it's a bit of a weird setting, right? So you are there, you don't a priori know what the exact answer is, and the way you would say that you're doing the right thing is to find some classical approximation method that does well enough so that you actually are close to the classical approximation method. So at that point, you can't say, oh, we beat the classical approximation method. No, you try to build confidence in that, right? So the next thing is, we haven't lost it yet. So of course, we're not claiming that you could ever run on these small scale noisy devices, something like Shor's without fault tolerance. I know there has before fault tolerance in the title, of course, that's not what we're claiming. And the third thing is, we're not that married to the Ising model either, right? So I don't think the utility or the usefulness of this experiment comes from the fact that we simulated an Ising model and that is more useful than a random circuit to some extent. That's not it. The goal is you have to pick some model that is easy and basically see on that model that's easy that you're actually doing something reasonable. And the utility in that sense is that this builds a proxy for a new method that you can use for different circuits now, different expectation values and so forth, right? And the essence is that by now, many people have proposed methods that are supposed to work with this confined circuit framework. And this is exactly where you would want to use these newer devices to actually explore and see which ones hold up, okay? Okay, sorry. Right. So what made that experiment possible about a year ago? So the first thing is, of course, you have to build a reasonably large system of 127 qubits. There's been a progression. So actually, we started running experiments all the way back on 4, 27, 65. Those we actually never published, and then the 127. Right. The next thing is you can actually really see that the hardware team puts in a lot of effort and actually was able from same chip layout, Eagle R1 to Eagle R3, to drastically, well, reasonably drastically increase the coherence times. And so that was actually, okay, that's the first time we'll take a stab. The next thing is people came up with new calibration schemes that are a lot more efficient, they'll work a lot better. And lastly, what I probably talk most about, we have a very, very, very simplistic and simple noise model, which works surprisingly well in this context. And we were able to use that and exploit that in this setting, okay? So what we did before, without having a proper noise model, was the following. So you can do Z and E, for example, without having to write down or know what the actual noise model is that you're working with, right? So what we used to do beforehand is you make an assumption. That assumption is, okay, my coupling to the environment is sort of constant. I have a constant coupling to the environment. And given that promise, what I can do is I can assume I can now perfectly modify and stretch my circuit so that over a different time period, they basically implement the same unitary, but the time of noise exposure is longer. So we call that gate stretching. And that's how we used to do this, but that becomes extremely painful if you go to larger devices, right? So what do we do now, right? So we basically come up with a sort of sparse noise model, and I'll walk you through that now. So right. So what we want to do is basically, okay, so we're making an assumption, okay, there's a bunch of gates. We have some clean gate layers that are correlated and so forth. The two qubit gate layers, they're all bagged in there. And then we have single qubits. So for now, we assume those are basically relatively noiseless relative to the larger one, okay? Then we use Pauli twirling to turn this entire thing, every gate layer into this decomposition where you assume you have a theoretically correct C0 gate, and then you have a Pauli noise model, right? Which tells you, okay, so this is your decomposition. So your noisy gate layer is now U tilde preceded by some generic Pauli noise model for starters. So, Joseph talked about Pauli noise model previously, so I won't do that much. But so the assumption is, okay, it's just a mixture of classical Pauli errors. So you could have started with unitary errors, with other errors, with whatever. We have to make the assumption that it's Markovian. You have to make the assumption that it's sort of reasonably constant, and we'll have to make some other assumptions too, which I'll tell you in a bit, right? So in principle, what you could do now is basically, okay, having someone suppose someone writes down that noise model, I could now take some matrix power of that noise model where the matrix power is either -1, I go compute the inverse, or I can actually crank it up to arbitrarily long. And so that gives me a knob which either allows me to do PEC if I use it at -1, or I have a knob where I actually start increasing the noise by some factor alpha, right? And what that effectively means is, okay, we need to have some way of writing down what that power is of that matrix, right? And so that poses a couple of challenges. So in principle, what you have is now, so this is a Pauli model. It's completely determined by 4n real numbers, right? The Pauli fidelities. And then I want to compute some inverse of that. I know in which basis it's diagonal and so forth, but this is computationally not quite tractable, right? If you want to do that in general across the full device. So what we do is we have to make some sparsity assumption on the noise, right? And so the sparsity assumption on the noise that we make is basically, oh, we're just going to go and parameterize the noise channel in terms of a Lindbladian. So we don't believe, to clarify, that this is the genuinely true noisy evolution of the Lindbladian. What we're just going to say is, oh, after we twirled, we're promised that it's Pauli, and we pray that we're sufficiently close to the identity, right? Otherwise, this wouldn't make much sense. So it's sort of, your noise channel is close to the identity, but slightly perturbed away from that. And then that we parameterize by some Lindbladian in the exponent, okay? So not all Pauli noise models can be written that way, but given our assumptions, that should be okay. And so now what makes that model sort of efficient, or what makes it sparse is the following. So what you can do is basically you say, oh, let's only look at that expansion of the Lindbladian, basically say single body terms, two body terms, three body terms, four body terms, but roughly there. So if you say there's k body terms, then the number of parameters that determines that model is roughly n to the k. Okay, in our case, what we're going to use in the experiment is just two body terms, especially the ones following this coupling architecture. So it's actually only a linear number of parameters in the noise model for the full thing, right? And so there are other sparse characterizations. So one Joe Emerson mentioned earlier, which was basically you can make, for instance, so that's from a paper from Flamia and Wallman. You can make an assumption that your distribution is sort of looks like a Gibbs distribution, and you can learn local patches, and then by Hammersley-Clifford reconstruct that distribution. We wanted that one because it's so simple to work with. So why is it so simple to work with? Well, the noise model actually ends up having a very simple product form, even if you started just with a Lindbladian. So why does that happen? Well, if you look at these Lindbladians, so by composition, taking the compositional product, they basically commute, which means that that's this exponential factors, and you can basically integrate every Lindbladian by itself. And so you basically have a product of single flip Pauli channels that give you a correlated model. So it looks like a product, but it's sort of a compositional product, so your actual model is still correlated, right? And the original parameters basically, so it's either, okay, with probability omega k, leave it be, with probability 1 minus omega k, just hit it with an additional pk, and you take the product of those, right? Okay. So why is that such a neat model? Well, because if you then go and compute the fidelities of the model, so the eigenvalues, they have just a very simple exponential form. So now if you have a method that gives you some reasonable multiplicative error approximation to fidelities of a Pauli channel, choose your favorite method, then you need to essentially learn a polynomial number of those Pauli fidelities. And then what you can do is basically, so you can learn them by some exponential decay. So there's some nice bounds by Flamia and Wallman again, which basically decay, and you basically get, under some assumption on the size of the fidelity, you get a multiplicative error approximation to that. Then what you can do is you can basically, if you collect sufficiently many, depending on how you define your noise model, in the ideal case, the fidelities and the parameters that you have to learn, they're sort of related this way. Okay, by a linear relation, log fidelities and so forth. And so you can actually then recover them by running a non-negative least squares. So the only constraint you get to impose now is basically you don't have to renormalize that you end up with the proper state. The only thing you want to have is that all these lambdas are non-negative, and then you do a sparse recovery on them. So that was, for instance, an experiment that's from another paper on 4 qubits. And well, those are the noise coefficients that we learned. Following, basically, you have connections 1, 4, 7, 6. You have singles, and then you have all these 2 qubit guys there, right? And so the first sanity check of, is that actually a reasonable noise model, is the following game that you could play, right? So you can look at those fidelities, learn a few of them, recover your noise model, and then basically say, am I able to predict the remaining ones from my noise model? In that example, yeah, that's what we do, and it looks reasonable. Well, it's only for 4 qubits, but fine. Let's start simple. Okay, so the green one, the measured one directly, then we fit one, and then we basically check the other ones, the remaining ones, basically, do they fit? And yeah, they look decent, okay? So, but the other nice feature of that noise model is, so if you can manipulate that pretty easily. So you can raise that noise model to sort of an arbitrary power if you like. Yeah? Yeah, so that weird notation, right? So it's a placeholder for me to plug rho in. So that's what it is, right? So it doesn't do anything, it just has rho. The only thing is sort of, this is the compositional product, so I have to multiply it. This is why it's a bit awkwardly written, yeah, sorry. So an arbitrary power alpha looks, so negative alpha you can include with a sign. So as soon as you sign here, it's no longer a TCP map. But then you can basically update those omega k's, and you have some prefactor gamma alpha, okay? So if alpha is greater or equal to 0, that prefactor is just 1, so you're amplifying noise, you're still working with the proper channel, but as soon as you go negative, you basically incur this exponential prefactor per layer that you're running with. Okay, and so how do you sample from that map? It's also very easy. You just have to toss order k many coins, basically with probably omega 1 minus k. So either I apply it or I don't apply it. You go all the way through. You keep track of the signs. If you're implementing the negative one, you go multiply that quantity out, and then check the parity, multiply the minus gamma, and you go multiply that minus gamma with the output times the output observable, and you insert this perturbation into the circuit, which you can basically combine with the other Paulis that you randomly insert all the time. So effectively, this is just a way that you classically resample the random circuits that you had originally. So you had all those random Paulis that you're starting to insert, and now you basically shifted the distribution a bit by adding these terms on top of this. And you get to multiply the output with minus gamma for the case where you have some PEC type thing, or you leave it be otherwise. Okay, so that said, let's go and talk about the second sanity check. We'll just run PEC for a very small system and see whether it does what it's supposed to do. All right, so in that case, smaller experiment yet. So this is going to be a 10 qubit experiment. You can learn on 27, but that's the first 10 qubit experiment. What you do is, okay, standard thing, as simple as it gets, transverse field Ising model. And what we do here is basically we allow various different gates, have 2 C0 gates, insert an RZ rotation, you repeat those layers, insert some single qubit rotations basically given on that. So it's, I was told it's called a kicked Ising model. We called it always poorly trotterized, but it's essentially the same. And you can run this, and then you can do some sanity checks. So the first thing you want to do with PEC as a sanity check is, okay, this is supposed to work no matter what, if your conditions on the error hold, right? So if your noise model is the right one, and you invest sufficiently many samples, you can do whatever. So let's pick the most noise-sensitive function that we're aware of. Let's take parity across all qubits, so it's a product of all z operators, and track that as a time evolution of the Ising model. And so what you can see here is basically, say, let's do this for weight 10. You start out in sort of the all zero state, and of course that's all one and everything is fine. I mean, there's a lot of cleanup that's already going on in that signal. So we do Pauli twirls, we do readout mitigation, we do so-called dynamical decoupling sequences, and after all those steps, you roughly get this curve, right? And after a couple of steps, you start at 1, you bounce down to 0, then it goes back up, and the theoretically correct curve should be that dashed line, right? And even after, I don't know how many, 1, 2, 3, 4, 5, 6, 7 poor Trotter steps, we're pretty much gone, right? So now the cool thing is with PEC, you actually recover that, right? So the inverse sampling of the entire thing, you recover what the ideal one should be, and those error bars are actually the correct error bars from theory that we have from the entire thing, okay? So that again, however, is only a 10-qubit experiment, okay? So, and that's not what we do in the utility paper either. What we do is basically, we want to see, right, let's get there. So in the utility experiment, we basically go and expand that entire thing. And so we do, again, the old trick of the poorly Trotterized time evolution. And what we do is we say, okay, let's just make sure we want to have the first data point that this actually does something meaningful and reasonable, right? So you start the evolution from some initial trial state, all zeros, then you choose varying circuit depth. So we're plotting different curves for different circuit depth. First depth 15, depth 6, and then the last one is 1 data point at depth 60, right? And so what we do is basically we have one parameter, and we say we uniformly apply that parameter across all the local X gates between every layer. And then we sweep that and just want to see, can we correctly predict that curve? Okay, and so how do we set that up? What you have to, so this is roughly the layout of the Eagle processor, which is like this heavy hex lattice. So it's the closest. So what you have is basically it's a 3-valent and 2-valent lattice that connects, right, roughly. And so that means you have to have at least 3 layers that differently that cover it. So this is the covering layers of 127 qubits, which means you have to, what we use is, so we choose a rather large step, there's like 3 different ZZ layers. So which means we have to learn 3 different noise models. Okay, so so this is 3 different noise models where we still have this linear approximation, that noise model. So we have single qubit, single qubit Paulis, 3 of them on every vertex. And you have basically the full set of the 2-body Paulis following that coupling topology. So how long does that take to learn that thing? So now we have this sparse noise model and so forth. We want to go and recover it for 127 qubits. So there's in the order 127 times some constant many parameters that you have to learn. The neat thing is, because it's following this local coupling topology, there's a covering between different Pauli fidelities that you can write down that allows you to basically only do 9 basis measurements independently of the system size. So across the full chip, 9 basis measurements, you start recovering a lot of Pauli operators from those. And from that, you do the sparse recovery and so forth, and then you end up with the noise model that you work with. That entire protocol to actually learn that noise model, the way we've done it, takes about half an hour. And then the question is, so how long does that last? And what happens is basically the device drifts and so forth, and within that time, you have to run. So, we have about 8 hours roughly that we run and sample and compute the data. So then the circuit that we do, I'm realizing I'm a bit short on time. The circuit that we do is basically just 1 RZ at pi half. So it's just a CZ gate. And so it's a Clifford circuit at the points where theta equals to 0, where you just run the identity. So it's a trivial circuit where everything compiles back to the entity. At pi half, they're sort of almost, they're again Cliffords. So those 2 endpoints of that circuit sweep, they're Clifford circuits, and then in between, you're not, right? And so what, let's talk about that. So our motivation now is, we want to establish that we get to produce correct values, right? That's our goal. So we asked for help. by Sajant and Mike. And so they use two simulation methods. I'll talk about the newer ones later that people have brought up. So the one was first the matrix product simulator. The second was ISO-TNS, which is essentially a PEPS, but with symmetry constraints. And then we say, okay, let's go to somewhere. Let's go small first. Let's just do 15 layers deep, and let's try to look at what the experiment says or does. Right? So then in that case, the noisy expectation values are the green ones. Then the mitigated ones are, after we applied procedure, are the blue ones. And then we want to compare to MPS and ISO-TNS to see that we're correct. Right? And it turns out they disagree. And but in that case, one has to point out something. Our circuits are really simple, right? So they have the property that every Trotter layer, basically, they're commuting CZ gates. So every layer you step, you only go very one step in width. So they're actually rather shallow in that sense, right? And because those CZ layers, they're commuting, right? And so you can exploit that to actually compute what it does exactly. And so what you can do now is you can basically compare the exact curve, because you have a very narrow light cone of this entire thing. You can compare the exact curve with the mitigated experiment. At that point, we say, okay, we can't really rely on the predictions of MPS and those ISO-TNS methods anymore, because they already fail here. Okay. So going further, you could say, okay, this was just for the average magnetization across the chip, which is sort of average over a bunch of one-body observables. All right. So the first question is, and it goes to 0, right? And so you could, well, maybe it goes to 0 because you're just depolarized at that point, right? You already 15 layers in deep. No, but then the first thing you can do in this setting is, okay, let's do the next one. Let's pick a stabilizer. So we know it's not the stabilizer of the identity of this guy, but here it's the stabilizer of the other circuit. So we know that should be 1, this should be 0. And it still has a very narrow light cone. It just goes up to 37 qubits. And you basically have this evolution, and now you basically, again, we're pretty close. Oh, it's not perfect. There's fluctuations and whatever, but we're pretty close. Seems reasonable. Whereas, okay, they're already, both those methods, they fail, right? Okay, so you really can't trust those. Same game, you go a bit larger. You go pick a even larger stabilizer that covers 68 qubits. So what you can do is, how do you still get the exact one? Well, you can do a certain, if you're smart and reorder your tensor network contraction, you can actually get an exact contraction that covers these 68, right? And so, right, okay, our error bars are getting bigger, although one has to say basically those error bars, they mean only so much because they're basically bootstrap error bars. Because this is a heuristic method, we don't really have any formally proven error bars for those, unlike for PEC. Okay, and so now we enter a point where we say, okay, we can't immediately contract it exactly anymore. So we'll have to actually start relying on approximation values. And so we say, okay, let's do this. So these basically, they fail. We realize that, and so forth. And now we have curves that sit there somewhere. Okay, and there's different things people tried. We tried and so forth. So, okay, fine, let's go with this. Given the previous incidences that we did better than matrix product states and ISO-TNS, given those, we figured, okay, we trust our device more than both of them. Okay, so then it took about a week or two, and people brought up classical simulations of the device that did better. Okay, so if you compare the first one that came out was actually by the Flatiron Institute. And that one had us actually a bit nervous, because they did the following thing. So their method worked peachy fine on all the lower, on the smaller shallow circuits where they're working. They really recovered what the exact curve was as well, unlike MPS and unlike the ISO-TNS. But then their curves for the larger devices did something that our experiment didn't do. And so basically they were, at the end, basically they had this tail in here. Right, so my new tail, considering all those fluctuations, it had us worried that, since this is now a circuit at depth 60, 127, and we should recover we're recovering a 0, maybe we're actually already in the weeds, and so we can't say anything anymore, and so forth. And what happened then was basically, it didn't take much longer. There was the second paper that came out, which was Garnett-Chan's paper, and they did something called the Clifford perturbation theory, and that actually relieved us, because that one actually dips down to 0, and exactly at the point sort of where you wanted, where we wanted us to also be to 0, right? And so one has to say, so the Flatiron people, they basically massively improved their method, and so the plot that I initially showed you was actually from them. And so in that plot, you basically have, I think, in total of 11 methods, right? So those bad ones initially, those are from the ISO-TNS, the MPS, but now you have all these other methods as well. So there's a direct matrix product state operator. There's the Google one that simulated 31. There is the improved one by from quite some time later by Garnett-Chan's group, where they also do belief propagation and combine that with the other one. There's the improved one from the Flatiron that gets really clear, that sort of agrees with the belief propagation from the Chen one and so forth. And now you're sort of in that setting where we actually want to be, right? So just for comparison, I can tell you what our personal nightmare scenario would have been. Our nightmare scenario would have been the following. So that basically we come out with that curve, and then people start simulating this thing, and they produce all curves that perfectly agree with each other, but sit somewhere else and not where our device sits, right? And so that fortunately didn't happen. But there's some interesting other point to this. So why do we say we're sort of beyond exact or so forth? So we can clarify that point as well. The point is, so within each of those methods, none of them has a formal ironclad guarantee. So you play the same game that we're always wanting to play, what computational physicists plays. You bunch a bunch of methods together, and after a while, they start agreeing, and you say, okay, fine, that's fine, right? And so you can only say basically stuff that, okay, that within my method, I have converged, right? Meaning, so you have a certain parameter that costs you, say, I don't know, bond dimension, size, whichever it is. You basically start increasing those, and within that, you don't see any change in error, then you declare it has converged. Is that the exact answer? Well, you don't know. It might be, it might not be, right? And so forth. So, and that's sort of the situation where we're at. So, all right, so there's a hiccup in my slides. Let me go to the, skip this. Oh, no, that's fine. It does the right thing. Okay, so what's next for us? So what we actually want is we want to have error bars. So subject to reasonable assumptions, so that reasonable assumption being that our noise model is actually the right noise model, right? So if that doesn't hold, then well, okay. It could be non-Markovian, there could be other inferior systems. So, but subject to those, what we would really like to have, where this is sort of the next step, would be that you go beyond approximation methods and you can actually give a certifiable guarantee that your expectation value does something or does this thing, right? The other thing is now, this is actually a really, the way we see it, this is a really nice new tool. So you can do many things with this. You can now run circuits, estimate expectation values. At least for one case, we know it worked, right? And so the question is then, what would you like to run on this? Or what would you like to see run on this, right? So from a meta perspective, that's something that we actually argued in the introduction, is we sort of want to disentangle the argument that is sort of innate to sort of some supremacy argument initially, right? So in a supremacy argument, you run that experiment to stick it to the doubters, right? That's why you run it, and you're fine if your device does something in some reason in a well-defined problem that you can't do classically, right? And it doesn't really matter of whether that's useful or less useful and so forth. And what we're trying to do here is sort of take those two steps apart. So the first thing we want to know is, we want to have a device that does something reasonable and we can start trusting it. Now, the second question is, so it works only within the confines of, okay, it is that noisy, it is that large, so find something that fits there. From the question of what is it actually useful for, in the sense of, can you actually obtain an advantage? So can you find a problem that neatly maps to our problems and so forth, in which you then basically harness a quantum advantage. So we only do the first thing, right? So we only care about, do we have a device that actually does what it's supposed to be doing? Okay, and so what then happened is basically, not shortly after, but like over the course of the entire year, there's many, many more 100 plus qubit experiments that came out that run on that run on that device, and especially also on the newer devices, right? And so there's various, and they're all physics motivated, one has to say here at this point. So there's some that actually utilize measurements. There's other ones. And so what we can see actually is exactly, okay, people could use this as a tool and try things out on those devices and see how well they do, right? Okay, and then lastly is there's now, of course, an evolution in those devices, right? So they get progressively better and so forth. So we have a newer one, which is this 133 qubit processor, which is the Heron. And what happens is basically in the Heron, at least if I trust my experimental friends, they're ecstatic because there's many things that work a lot better on the Heron than they did on the Eagle device. Okay, and so we're running some early experiments on those as well, and you can have actually a significant improvement, factor of 2 to 4 in gate fidelities and so forth. But is that sort of the end or the limit where it goes? And so there are some hardware improvements that are sort of pending by if you look at individual components, right? So they're not on chip. The gates are, but the coherence times aren't. And people in the lab, they actually start building coherence times of single qubit chips that sit beyond the 1 millisecond range and actually 3 millisecond range and so on, right? So I can talk about that stuff because I think Jay tweeted about it, so it's fine. I'm not disclosing anything illegal, right? And so that is really that's really optimistic. So that's of course standalone single qubit chips. The other thing is basically the best 2 qubit gate fidelities, they're really at the 10 to the minus 2, right? So these were basically our curves in our curves in from the Eagle devices, and you have an order of magnitude better 2 qubit gate fidelities and times, right? So with that, I think I'm at 4 o'clock and open for questions.
Thank you very much, Kristan. Questions? Let's start in the back.
Hi.
Hey.
Yeah, you know what I'm going to ask.
Sure, go ahead.
So, I think it's important to consider not just the light cone, but also, the butterfly cone or whatever you want to call it, which is the gates that actually influence the observable that you're measuring, which is why you only need, 31 qubits to
simulate that.
To simulate this.
To find an approximation. So we said, 31 qubits to have some approximation that looks reasonable for that circuit, right? Because there's a couple of things. So, I mean, we talked about that earlier, right? And how you define that, what actually the effective is, and so forth, right? And so it might be that we don't see an eye to eye on that one and how you properly define this, right? But fine. But in principle, yes. So in principle, you have. What we're doing here is essentially an experiment where you say, okay, this is our device, this is how well it runs, and this is why there's multiple reasons of why you want to run it that way, right? So the first thing is, as I said before, the model that we use is very, very simple. So in principle, you could imagine, okay, the next upcoming versions of the model and so forth, you want to crank that up and so forth. And also the device hardware is getting better, okay? And but there's many things you can do, but the question is why you want to do them, right? So so you can a priori say, in theory, you know exactly what device should be doing and so forth. And in theory, we know that error mitigation works as well. But the reason for us to run those experiments on a feasible circuit that works well is specifically to actually try out how well that holds up in practice. And so there's many reasons why we set it up this way, right?
I think it's a very impressive result. Thanks for the overview. I was just wondering, a key piece was learning the Pauli errors and making some assumptions about the correlation properties and so on. I'm wondering if you had a chance to compare the new tunable coupler chips with the older chips that had crosstalk problems, and if you see a big improvement in the ability to kind of capture the full noise model that way.
I don't know whether I can comment on that. I honestly don't know. So I know that that's exactly what they're looking at the moment, and especially also in the context of the noise model. But I don't know what I'm supposed to know there and whatnot. I'm sorry. It's just a stupid answer, yeah. But
Yeah, I have a follow-up question, which is like, I mean, you make this kind of a sparse Liouvillean model for your noise.
Mhm.
I mean, have you tried, and can you try like Liouvillean learning techniques to kind of see to what extent this is actually a good model for your actual noise? And have you kind of certified that noise in your device?
So how do you mean Liouvillean learning technique, where you basically go and you try to learn? So again, I don't think so. In that sense, I don't think our model de facto evolves according to, oh, that's a unitary gate plus that Liouvillean.
Okay.
That only happens after you start twirling and you only start looking at the Pauli and so forth. And so it's just a parameterization. So I don't think that's the true noise of our device. It's just enough for us because we only care about expectation values, and there the average behavior is totally fine.
Okay, good.
Right?
Yeah, thanks.
Yeah, then I think.
How do you expect these methods to scale with higher degree connectivity devices? Because it seemed like the chip only had, what, 2.5?
2.5, yes.
So that's pretty low.
Yes, it's sort of 0.5 above 2, right? Which is a line. So that's a good question. I mean, that boils down to a matter of how much crosstalk you expect if you have that, right? And how much that basically how much you see the new couplers basically influence that. So again, if the new, so let's put it that way, if the new couplers do what they're supposed to be doing, then they should significantly reduce crosstalk, right? So I don't know whether they do, and I haven't seen any data on that yet, although I know that people are taking that, right? So in principle, so what you could do, so to answer that, there's a couple of things you could do. So first of all, so the noise model that we do, we just sat down and said, okay, it's just 2 qubit, right? So, but if that's bad, the first thing you could actually start doing is you could add more and more terms in that expansion to actually take into account nearest neighbor, next to nearest neighbor, and so forth. So that's one way to go. Other than that, I'm looking forward to the newer generations of chips which have higher connectivity. Then we'll know for sure. But otherwise, I'm just speculating right now. Yeah.
Questions? Last question or so? Yeah, over there.
You said that because you only care about expectation values, so it's okay if you just assume you can throw every noise into Pauli noise, right?
And some other assumptions about the noise, such as Markovianity
Right.
and so on and so forth, yes.
So let's assume that all those other assumptions hold.
Yes.
So for which applications is it not okay to assume that your noise can be thrown into Pauli noise?
So I'm not saying that it's so what I say, okay, let's put it that way. So what I think is that let's put it that way. We know for sure that it works because that's an expectation of randomized instances. But you could worry about the fact that you want valuable information of sort of a single trajectory. So of a single instance of a randomized circuit, and then you basically run through that trajectory. In that case, I don't know of basically whether in that picture where you basically now have that single trajectory and so forth, you insert a bunch of Paulis in there, whether that basically follows the correct statistics in that sense. So that I don't know. So that's a concern. So it's sort of a conservative estimate that we say we're for sure that it works here because, bar the other assumptions, because it's just an expectation value in that case, right?
Thanks.
All right, then in view of time, I would suggest to move on to the next speaker and thank first Kristan again.
Thanks.